Prim's algorithms and Kruskal's algorithms. And for Kruskal, we will also be studying we will new data structure DSU to efficiently implement Kruskal algorithm. And then we will discuss topological sorting of directed acyclic graphs using normal depth first search algorithm. First of all, what is the minimum spanning tree problem? In this problem, we are given a connected, weighted, undirected graph, and our goal is to find a spanning tree with minimum total edge weight. So first of all, what is a spanning tree? Spanning tree is basically subgraph of the given graph, which is a tree, as simple as that. So let's take an example. Say we have a graph 1, 2, 3, 4, and let's suppose the weight of the edges are 5, 6, 7, 8. So here 1, 2, 3, 4 is also a spanning tree with the edges of 5, 6, 7, and 2, 3, 4, 1 is also a spanning tree with the edges 6, 7, and 8. And our main goal in this problem is to find that tree among all the possible trees such that it has minimum total edge weight. And also there is one important thing in this algorithm, that if the graph is disconnected, then the MSG of such a graph doesn't not exist. Because obviously if there are more than two connected components in the graph, then there is not any possible subgraph possible in which those disconnected components become connected. So there are two algorithms there are many algorithms. We will be discussing mainly two algorithms, Prim's and Kruskal's. In Prim's, we basically select an arbitrary vertex and expand that vertex until it becomes a spanning tree by choosing minimum weighted edges. I think we should discuss example. We should first discuss example that how we approach it using Prim's algorithm. Say we are given this connected acyclic graph 1, 2, 3, 4, 5 with edges as given as follows, and we want to find a minimum spanning tree. So what does this Prim's algorithm says? That first of all, select an arbitrary vertex. Let's say we select 1, and then we will expand this vertex by adding edges with one vertex in the already selected set of vertices and other in the set of vertices which we have not selected yet. So there are two edges in step 1, that is this 1 and 3 weighted edge. So in order to expand 1, we can either add this edge with weight 1 to it or 3. This algorithm says that we should choose the edges greedily. So we will expand our subgraph by adding the minimum possible edges. So we will first add this one edge weighted 1 to this graph. So now our subgraph is just this 1 and 2 connected by this edge. And we have to select out of these 3 edges in order to expand this subgraph. And as 2 is the least weighted edge among these 3 vertices, so we will select this 2 edge. And now we have 2 more edges options available. And similarly, now the next smallest possible edge is this edge with weight 3, but as it has both of its ends in already selected vertices, that is 1 and 3, we will not choose this edge, because else this graph will become cyclic and we just want to get a minimum spanning tree, that is acyclic subgraph. So out of these 3 edges 5, 4 and 7, we will choose 4, and out of this 6 and 7, we will next choose 6. So our minimum spanning tree here becomes 1, 2, 3, 4, 5, connected by edges weighted 1, 2, 4, and 6. We can see here that first we chose the edge 1, 2, then we pick edge 2, 3, then 3, 4, and then 6, 5, and then we got our minimum spanning tree using this algorithm. And now we will learn how to implement this efficiently. Yes. So basic intuition is that for every unselected vertex, we store the cheapest known edge to the tree. And there are two ways to implement this algorithm. One is the dense version that we implement for dense graphs, and the other is the sparse version. Dense one has the complexity O n square, and the sparse one has complexity of m log n. And we will discuss this complexity in detail later in this lecture. So for the dense implementation, we basically just store the cheapest possible edge known for every unselected edge in Mini. And basically, we like iterate for n times, and where n is the number of vertices. And in each iteration, we select a new vertex G, which is not yet used and has a weight less than the current chosen edge V, and then we will add that edge to our connected component, and thus we can expand our selected subgraph in n iterations. You can check out this implementation later by implementing it yourself in your local systems. And for the sparse graph implementation, we simply maintain a priority queue where we store a pair of weight and edge V and vertex V. And if that vertex is already contained in our selected subgraph, then we skip that. Obviously, then we will not add that weight, else it will become a cyclic, like we did in an example. But say like we have already selected this subgraph 1, 2, 3, then we will not add this edge 1, 3, else it will become cyclic. So we simply skip that, skip the loop in that case, and else we add that weight and add weight W in our total weight. And this we will get our spanning tree in m log n complexity, because this loops runs for m times, and for getting top element of the priority queue, the complexity is log of m. Yes. Yes. So now we will discuss like why this algorithm works. So in our case, say our graph was this with the weights 7, 8, 9, 10, and 11, and we were forming our minimum spanning tree by adding edge greedily and expanding an arbitrary selected vertex, say 1 in this case, and we selected say 7. Yes, so this is our minimum spanning tree. So our claim is that by selecting the smallest, selecting the smallest weighted average, smallest weighted edge in each iteration, we get an MSG. Say there exists another. say there exists, uh, say in an iteration, let's say the first iteration, there exists an edge weighted, there exists an edge A such that it is not selected, but our algorithm says that we are choosing the lightest crossing edge and it is the lightest. Yeah, basically, say Prim chooses an edge A that is not in some fixed MSG, and in that MSG, the path between the same two components must contain another edge F crossing the same cut. So in this case, there exists another edge, this weighted 7, let's say it was F, and it was crossing this cut. And uh, since Prim always chooses the lightest crossing edge, the if even if we selected this edge, which whose weight is less than equals to our uh, uh, edge of which is contained in MSG, the overall weight will only decrease and will not increase. So if we select our edges greedily, we will get a minion spanning tree. So yeah, and I think it is very intuitive. Yes, so now we will discuss Kruskal's algorithm. In Kruskal's algorithm, we basically sort all the edges by weight, and if our shortest possible edge, if one end of the edge or shortest weighted edge lies in different connected components, we will simply add that edge as it will connect two different connected components. And if both the ends of the smallest possible weighted edge lies in the same connected component, we will remove that edge because else it will form a cycle and we need a subgraph that is a tree. And I think we should also check it by example. Basically, we will sort all the edges by weight and then we will add edges one by one such that these new edges doesn't make any cycles and add two different connected components. So here, shortest possible edge is 1. So in first iteration, we will simply add this edge 1. Then shortest possible edge is 2. And again, both ends of this edge lies in different connected components. So we will add this edge 2. Now the next shortest possible edge is 3. But for this edge, both of its ends lies in the same connected components. So we will not add this edge as else it will form a cycle. Then the next shortest possible edge is 4. We will add this edge to our in our MSG, and then the next one is 5. So thus we get our MSG as 1, 2, 3, 4, 5, and we can show that this tree has the smallest weight sum across all the possible spanning trees. Yes, okay. Yes, yes. Yes, initially we start with n different connected components where n is the number of vertices. And as we add edges one by one, we decrease the number of connected components by one in each iteration. So yeah, here the number of connected components are 4. We added the edge 1, 2. Then here we add edge 2, 3. Then we will skip 1, 3 because it forms a cycle. Then we will add edge 2, 4 and then 3, 5. And now we have got our MSG, so we will stop our iteration here. So our main task here is how to check if our edge connects two different connected components or lies in the same connected components. For this, we will discuss a new data structure which is known as disjoint set union, DSU. What is this is, let me give you an overall idea of what is this data structure. Say I have a set of numbers from 1 to 6, 3, 4, 5, 6, and I distribute it into three sets. One is 1, 2, 3, the other is 4, 5, and the third one is 6. So using DSU, I can efficiently check if any two chosen numbers out of this list lies in the same set or in different set. For example, I choose one, I want to check for 1 and 3. So this DSU will tell me that if these two chosen numbers lies in the same set or not. And how it is done, that in DSU, which basically store a representative for each set, and that representative is same for all the elements of the set. For example, representative of this set is 1, so, and representative of the set is 4, and representative of this set is 6. So if I want to check two queries, say 1 and 2, and the other is 1 and 4, that whether these two vertices lies in the same set or not, I can simply compare their representatives. If they have the same representatives, it means that they are in the same set. And if their representatives are different, it means that they are in different set. Here, both the representatives of 1 and 2 are 1, so they are in the same set. And for 1 and 4, their representatives are different, so they are in different sets. So yes, in DSU, we can make three operations. Make set V, which basically makes a new singleton set containing only V. So if I call make set 7, I will get a singleton set 7. Find set V will return me the representative of that element V. So if I call find set 2 or find set 1 here, I will get 1. And union sets A comma B merges sets containing vertices A and vertices B. So if I call union sets A comma B for 1 and 4, my final set configuration will be 1, 2, 3, 4, 5, as I have merged the set containing 1 and 4, and there will be another set 6. So these are the three operations carried out by DSU. And we can optimize DSU mainly by two methods, by path compression and union by size. Basically, path compression is basically DSU in computer is stored as a tree where we store a parent of each vertex. Say 1, 2, 3 is stored, maybe 1, 2, 3 is stored like this, 4, 5 is stored like this, and 6 is stored like this. And the representative of this set is basically the topmost element of this tree. So what we can do is when I call find set of 3, I can simply remove this edge and directly point it to 1, so that when I call find set 3 again in the next iteration, I don't have to iterate it to 2. I will directly get 1. You will understand it better when we discuss the implementation of it. So yeah, basically in DSU, we store parent of each vertex for each set. And when I call find of any integer V, I will basically set that I will basically change that parent of that element to the topmost element that I did in the example. Say it was 1, 2, 3, and I call find of 3. It will return 1. So before returning, I will set parent of 3 equals to 1. So instead, so in the next, if I call it again, in the next time, it will again directly return me 1 instead of going it through 2. And unite AB basically just unites using the For Unite AB, basically we set parent of one set to the parent of another. For example, in previous case, we had these two sets 1, 2, 3, and the other was 4, 5. And if I called unite 1 comma 4, I will simply set parent of 4 to 1. So now, if I call parent of I for any of the integers of this set, I will get 1. So I have basically done the union of these two sets. And thus now Kruskal can easily be implemented using DSU, as we can almost find in O of 1 that whether two vertices A comma B are lie in the same set uh, or different sets. And we just need to sort the edges and iterate it one by one. Yes, the complexity is m log n because the number of iterations will be m, and yeah, sorting takes m log n time, and the these operations are almost constant amortized time. So the main difference between Prim's and Kruskal's algorithm was that in Prim's algorithms, we expand our selected spanning tree. For example, we had one, then we. Yeah, so main difference between Prim and Kruskal was that uh, in Prim's we expand our selected minimum spanning tree, and in Kruskal's we had initially many different connected components, and we reduce the number of connected components one by one. And yeah, complexity for Prims is O(n) square for dense and m log n for sparse. And for the Kruskal, it is m log m with DSU in any case. Now we will discuss topological sorting. So what is topological sorting? In topological sorting, we are given a directed graph, and we have to find a permutation of vertices such that every edge goes from an earlier vertex to a later vertex. Let me try to explain it using an example. Say we are given this directed acyclic graph 1, 2, 3, 4, 5, 3. Yes. So if I take the permutation here 1, 2, 4, 3, it is a topological sorting because every edge, for example, 1, 2, 2, 3, 4, 3, and 1, 4, lies from a vertex to the left, from to the vertex to the right. And if I take a permutation such as 2, 1, 4, 3, it is not a correct topological ordering because there exists a back edge here from 1 to 2. And also there can be multiple topological orders for the same directed acyclic graph. That is basically it is not unique. As here in this case, 1, 4, 2, 3 is also a correct topological order. And now how to get a correct topological order? The intuition behind is that for every edge u to v, the vertex u must appear before v. So basically, we want a linear order such that for every edge, the left vertex lies earlier than the right vertex in our permutation. And also, we can only find topological ordering for acyclic graphs. For cyclic graphs, such an ordering is not possible because there will always, because in all the permutations possible, there will always be an back edge. For example, we take 1, 2, 3 here, and if we take any permutation here, 1, 2, 3, as it has a cycle, there must exist a back edge. So there is no topological order possible for directed cyclic graphs. The main idea to solve this ordering is that we will solve it using DFS. What is DFS? DFS was depth first search that we searched for the deepest possible element first, and then we went for the other elements. And basically, we will perform DFS for all the vertices, and then we will reverse the list. Let me explain it using example. Yeah. For example, let's say I perform DFS here. Then what I will get is, uh, first of all, I will call DFS of 1, will call DFS of 2. Of 2, it will call DFS of 4. And then at last, it will call DFS of 6. So I will get 6, then I will get 4, then 2. Then after DFS of 2, DFS of 3 will be called, which will call DFS of 5. So I will get 5, 3, and 1. And I will simply reverse this list, and I will get 1, 3, 5, 2, 4, 6. And our claim is that this ordering is a topological order. I will show you why this is correct later in our discussion. But you can see that in DFS first we selected 6, then 4, 2, then 5, 3, 1, and then we simply reverse this list to get our topological order. And why we are doing is this? This is because when DFS of V ends, every vertex reachable from V has already been completely processed. So we must come after all of them in the finishing list. What this means is that for every edge V to U, if we perform a DFS, U will always come before V. So basically, um, for this list, for every edge, our head will lie in the left and tail will lie in the right. And we simply just need to reverse this list to get our correct order. And after reversing, all edges will point forward in the correct topological order. Yeah. So the main idea is basically for every edge V comma U, U will be visited before V in the DFS. So we will store U first before V, and then we just need to reverse the list to get our correct answer. So that is it for topological sort. And these are the complexities of the algorithms that we discussed today. For Prims, it was O(n) square in dense form and M log n with the heap. For Kruskal, it was M log m because DSU is almost amortized in O of 1. And for topological sort, by DFS, it is O of n plus n. So yeah, I think that's it for today. Thank you for joining.